Take any triangle at all. Fat, thin, lopsided, it doesn't matter. Now split each of its three angles into three equal parts. These lines are called angle trisectors. Where adjacent trisectors from neighboring vertices cross, you get three special points. Connect them, and you get an equilateral triangle every single time. Pause and think about why that might be true. Let's set this up. Call our triangle ABC with angles 3 alpha, 3 beta, and 3 gamma. Why the factor of 3? Because we're about to trisect, so each third will be a clean alpha, beta, or gamma. Now here's the crucial observation. The angles of any triangle add up to 180 degrees, so 3 alpha plus 3 beta plus 3 gamma equals 180. Divide everything by 3, and you get alpha plus beta plus gamma equals 60. Remember that number. 60 degrees is the hidden engine of this entire proof. You already know angle bisectors from geometry class. They split an angle into two equal parts, and all three bisectors meet at a single point, the incenter. Trisectors split each angle into three equal parts instead, but unlike bisectors, the 6 trisector lines don't all meet at one point. Instead, adjacent pairs meet at 3 different points, and those 3 points form our mystery triangle. Your first instinct might be to use coordinates or brute force, but there's a much more elegant approach, the sine rule. Here's the game plan. We want the side lengths of the inner triangle DEF, and we'll show they're all equal. Start with the subtriangle ABF, where F is where the trisector's nearest side AB meet. The angle at A is alpha, 1/3 of angle A. The angle at B is beta, 1/3 of angle B, so the angle at F must be 180 minus alpha minus beta. But we showed alpha plus beta equals 60 minus gamma, so the angle at F is 180 minus 60 plus gamma, which is 120 plus gamma. Now apply the sine rule in triangle ABF. AF over sine beta equals AB over sine of 120 plus gamma. This gives us AF explicitly. Now here's the key step. Look at triangle AEF. We know AF from the last calculation. The angle at A is alpha, it's the next trisector line over. What about the angle at E? By exactly the same reasoning we used for F, the angle at E works out to 120 plus beta. Apply the sine rule again. EF over sine alpha equals AF over sine of 120 plus beta. Substitute what we found for AF, and watch, EF equals AB times sine alpha times sine beta, divided by sine of 120 plus beta times sine of 120 plus gamma. This looks messy, but stay with me. Here's where the magic happens. Using the identity for sine of 120 plus theta and the extended sine rule, AB equals 2r sine 3 gamma, where r is the circumradius, we can simplify that expression. After substituting and using the triple angle identity, every side of the inner triangle simplifies to 8r sine alpha sine beta sine gamma. Look at that formula, 8r sine alpha sine beta sine gamma. It treats alpha, beta, and gamma completely symmetrically. There's nothing in this expression that distinguishes one side from another. This makes sense. The formula only involves the 3 trisected angles, and they enter as a product, which doesn't care about order. So if we compute DF or DE using the exact same sine rule method, we get the exact same expression. All 3 sides of triangle DEF are equal, and that is the definition of equilateral. Morley's theorem proved, no matter what triangle you start with, the trisectors always create a perfect equilateral triangle hiding inside. Frank Morley discovered this in 1899, and it stunned mathematicians because it had been hiding in Euclidean geometry for over 2,000 years. Euclid himself could have found it. This interplay of angle division and symmetry shows up in crystallography, where molecular bond angles create symmetric inner structures. If you enjoyed this, like and subscribe for more.